Happy Monday. Hope everybody had a good weekend. Any questions before we get started? All right, so let's dive into it. So we have a little bit, I think this is technically from last week's chapter, oxidation reduction reactions. And so we at least want to look at this briefly for our knowledge. And so oxidation reduction reactions are just formally reactions in which electrons are transferred from one reactant to the other. And so we often call them redox reactions for short. And then many of them do involve the reaction with oxygen, but not always. And so we want to look and think of a few characteristic examples and types of reactions. And so to kind of go along with this, because this is pairs with the chemical reaction lab, if I can find it. And so looking at our lab, where is the PDF? There we go. So if we look back at our lab, so this is lab 5 and kind of that reaction type cheat sheet. So we can look at a few examples and then identify them as redox or not. And so you have this combination reaction. And so usually two things start off in their elemental form and then they come together, make a new compound. And so those tend to be redox. And so this is another example here, right? So formally, that's a combination reaction. Again, those tend to be redox. And then, of course, this is our classic combustion reaction. This is obviously a redox reaction. So combustion is always a redox. So same thing. So this is another. And we can classify these as either combination or combustion reactions. And so we'll put that as kind of other examples here. So we can, again, relate it to what we actually have seen in lab. And so another type, so our decomposition reactions, those tend to be redox as well, because again, you're going from one thing, and then in this case, back to its elemental form. So usually a good indication that that's a redox. And the states are what help you also determine, right, that it's back in its elemental form. So we said decomposition. So that's likely a redox. And then kind of the other classic example is the single replacement, where you have something swapping out. So they showed it where your halogens are swapping out, but we've seen this other example. So copper sulfate or any copper plus zinc with those metals, right? And then remember how it kind of made the rust of the copper. And so kicking a metal out or any single replacement is a redox reaction. And I'll write down the other one from your lab manual. So right, we can also have halogen exchange. That's another single replacement type reaction. And then if we kind of look at what's not a redox though, so then these double replacement reactions, so these usually are never redox reactions. And so you can kind of see for the double replacement, right, you're just swapping your cation partners. And that's really driven by precipitation, so not redox, or in the case of this one down here, the double replacement decomposition, where again, formally, right, they balance out, so you make H2CO3, but then that would decompose to give you water and CO2. So still a double replacement, so still no change in oxidation states. And so you might want to make a note of that. And so I would just say double replacement reactions are not redox. So that's kind of your quick and fast guide to redox. But then we'll keep looking at it right now. So let's look at kind of how we can tell. And so here's just another reaction. So hydrogen and oxygen, you can put them in a balloon. This is actually a demo, but sometimes I do. And then you set them on fire. It'll make a nice loud boom sound and also make a bunch of water vapor. So just like shown in this diagram. And so now let's kind of look at how do we know what's going on, and then how do we kind of analyze this. And so this is just kind of the setup here of what's going on. And so now it says to convert a free element into an ion, atoms must either gain or lose electrons. And then again, the idea with the redox is if something is losing electrons, right, the other one must accept them. And so then atoms that lose electrons are being oxidized, and atoms that gain electrons are being reduced. And so again, we'll kind of look at that. So before we look at kind of how to analyze, let's go over two little mnemonics. So I'm from Texas, so we were all about oil rigs out there, or oil. And so this stands for oxidation is losing electrons, and reduction is gaining electrons. And so you can use this, I often tell people, write it on your periodic table or something, a little cheat sheet so you remember. If you don't like the fossil fuel industry, I have another option for you. So I also know Leo goes grr, and depending on your school, or you can pick your favorite cat. I used to teach at an institution where their mascot was actually Leo the leopard. So I used to say Leo the leopard goes grr. So losing electrons, if I could spell electrons, oxidation, and then gaining electrons, reduction. All right, so that could help you remember. So let people write that down for a second. And so now let's analyze some of these reactions. So let's look at this one they have shown here. So we have sodium and chlorine give us sodium chloride. And so first we have to establish what their oxidation states are, which we should have kind of a set of rules here. So if we skip down to these rules, that will help us. And so the first rule is that free elements have an oxidation state of 0. So this just means in their elemental form. So how they're found in nature. So obviously, right, your halogens are going to be found as diatomics. And again, right, they're in their free elemental form. So as long as they are by themselves, they have an oxidation state of 0. And then once they're in a compound, then their ions will usually have an oxidation state equal to their charge. So again, if you need to write everything, do I have a periodic table? Let me grab a periodic table. And so your periodic table should have some charges on there. But again, just kind of remind yourself what they are. So group 1, right, they tend to lose 1 electron. So those are 1+ and 1+ oxidation state. Next one is 2+. And then these, right, 3+. And then carbon is where it gets weird because it can do the switch. And then nitrogen tends to be, right, 3- or 5+. And then our group 6 over here is generally 2-. And then halogens generally -1. So we kind of remember that, hopefully, back from our writing compounds. And then the sum of the oxidation states, of course, is 0. Again, assuming that you have a neutral product, which you generally will, but not always true, right? We can assign oxidation states for nitrate. And so then it mentions, right, the polyatomics. And so then the sum of the oxidation state of all atoms in a polyatomic ion equals the charge. Okay, well that, we already knew that. But then what you can see is this helps us figure out, so let's look at nitrate together. So NO3, -1. And so kind of going in priority of our rules, and it's also down here to kind of help us remember. But okay, we start with our free element rule. Okay, well we don't have any free elements, right, in a polyatomic. And then we start with our monoatomic ions. And so then we should base it off of oxygen. So kind of looking at this chart. So fluorine is always -1. So, right, it's the most electronegative. And then hydrogen tends to always be +1. The only exception are going to be metal hydrides. And hydrides have a -1 charge, or like iron hydride. So you might have seen a few hydride compounds in this class. And then oxygen, like I said, is almost always -2. So then we can base our compounds off of oxygen. So then going back to our nitrate, All right, well, we know oxygen is -2. -2 times 3 is -6. Overall -1 charge. So then nitrogen is formally 5+ there. And so that helps us. And then, let's see, it mentions this little statement here that, right, we assign our oxidation number. And so this is kind of a weird statement, but let's understand what they're trying to show us there. So, right, oxidation states are not ion charges. So ion charges, right, only apply for ionic compounds. And that just means that it's something that you can measure, right? So you can take your crystal structure, you could measure your charges of your different atoms, and they would have, right, those discrete ion charges. Once you get into these polyatomics, right, then we're just kind of using the oxidation states as more electron bookkeeping. So we can kind of tell who's going where and, you know, who's kind of donating electrons, who's sharing. But, right, it's not a measurable charge. And so really what we're saying is nitrogen has given up all its electrons to bonding. And then, so like we mentioned, next in priority, right, group 1 metals. So again, right, we expect them to have the 1+ oxidation state. Group 2, 2+ oxidation state. And then again, use this priority. So it mentions, again, fluorine always takes precedence. Hydrogen is always +1, unless we're looking at a metal hydride. Oxygen is always -2. The one exception is a peroxide, which is anything that looks like this, or hydrogen peroxide is the simplest one. But in a peroxide, the whole O2 has a -2 charge. So then each oxygen is -1. So that's any time you see a peroxide. But other than peroxides, oxygen should always be in the -2 oxidation state. And then, of course, the rest just kind of follow. So like we mentioned, right, group 7 is -1, group 6, -2, and group 5, -3, again, unless, right, we're basing it off something else like we saw with nitrogen. Questions on those, like, rules? Yeah, not the most exciting thing, although redox reactions themselves are exciting. And so again, this is kind of more definition stuff. So like we've seen in lab, right, they have to occur simultaneously. That's the whole point, the exchange of the electrons. And so if one atom loses it, another one must take them. And so now, right, we just did this oil rig and Leoger business, but we can also use other terms. So it says the reactant that reduces an element in another reactant is called the reducing agent, but then it's going to be oxidized. So then you might want to go up to your little mnemonic here and then remind yourself, okay, so oxidation is losing electrons, but then this is going to be my reducing agent. So again, your reducing agent is giving the electrons, but then that means it's going to undergo oxidation. So I'll let people write that because it's kind of confusing, right? It feels like it's opposite. And then scrolling, oh, are you trying to take a picture? Yes. Yeah, go for it. Sorry. And then going back, so then it tells us, okay, the reactant that oxidizes an element another reactant is called our oxidizing agent, but then this is getting reduced. So again, you might want to go back up here. And then, okay, reduction is gaining electrons, but then that means this is my oxidizing agent if it's being reduced. So again, just you need to write that down. Or all right, so that helps us kind of keep track of who's doing what. And so the other thing I like to think about is at least kind of put some context to these. So reducing agents, they tend to be our alkali metals. And so, right, we can start to think about, well, why is that? Well, the alkali metals, they want to give up their electron. And so they're happy to do so. So potassium, sodium, lithium, those are pretty strong reducing agents. And again, right, they tend to give up their electron. You can add that, right? They tend to lose electrons. So we can see that they'll be oxidized. And then any oxidizing agent, so obviously oxygen is an oxidizing agent, but then kind of our halogens behave similarly, so they're pretty reactive and pretty strong oxidants, so like fluorine, bromine. So again, just kind of thinking about the elements that tend to be on those extremes. And so again, we can go through this example. So sodium plus chlorine gives us sodium chloride. And so sodium starts off in its elemental form, so 0 oxidation state. We react it with chlorine, again, elemental form, right, diatomic, 0 for the oxidation state. Then they form their compound, so standard ionic compound like we're familiar with. So sodium, of course, is going to go to 1+. Chlorine goes to -1 since it's a halogen. And so now we can keep track of the electrons. So we have that sodium goes from 0 to +1 here. So if it's becoming positive, right, we can tell that it loses 1 electron kind of per sodium. So again, now we have to keep track of electrons. So however many we lose, we also have to gain. And so we have 2 equivalents of sodium, so really 2 electrons total there. And then again, chlorine, so each one goes from 0 to -1 now. So of course they're gaining 1 electron each. 2 electrons total in that process, though. And then just going through our formal definitions, of course, if sodium lost our electron, so oil rig, right, oxidation is losing, so it was oxidized, and then that means it was our reducing agent. Questions about this? So I'll probably do some more practice on that, but again, kind of the main thing I would say is this is our key takeaway of how to assign our priorities of our oxidation states, and then at least, right, you get some sense of how to determine that, so just comparing the before and after states. All right, so like I said, we can always come back to this if there are more questions, but then we'll start. So this is chapter 6 now. So energy, work, heat. So this is kind of our quick introduction to kind of thermodynamics and energy. So everything's kind of packed into this chapter. And so energy is just defined as a capacity to do work. And so energy is something that, of course, our object can possess, and we want to think about different forms of energy. And so energy can be exchanged through collisions, which we'll look at. And so, again, we need to just define some thermodynamic terms. And so work is just force over a distance. And so we could find the work by multiplying force times distance. So we won't look at too much work, admittedly, in this class. So especially the type of work for chemistry is considered pressure volume work, but again, that's kind of not here in this course. And then we, of course, will look at heat, though. So heat is just the flow of energy caused by a difference in temperature. So we'll kind of look at that in the context of exothermic and endothermic reactions. And again, define that later. And so heat and work are two different ways that an object can exchange energy with other objects. But like I said, we'll mainly be focusing on the heat part of that in this class. And so now we want to think about different types of energy. So of course, kinetic energy is the energy of motion. So kinetic energy, right, can also be 1/2 mv squared. So that's one formula, right, to quantify energy. Kinetic energy can also refer to the movement of electrons. So little electrons flowing around in circuits, so that's kinetic energy. And then thermal energy is energy, again, associated with temperature. So again, looking at that heat flow. And then we'll also be interested in potential energy. And of course, if you've taken physics, you might be familiar with gravitational potential energy, right? Energy due to position. Of course, we don't generally talk about that in this class, but we can talk about that. But usually, what we care about in chemistry and our potential energy is our energy in bonds, so kind of making and breaking bonds. You can also think about, right, your food. So hopefully you had at least a snack before coming to class. And again, right, so all those calories are potential energy that your body is then converting to mechanical and kinetic energy. And so again, just kind of recap. So we mentioned electrical, we mentioned heat. So again, those are kinetic. You can also have light energy. So we talked about that briefly. So just either, right, thinking about our flame test colors or the lamps. So again, right, those electrons coming back down, relaxing, and that gives off light energy. We won't necessarily talk about nuclear in here, or at least not too much. Obviously, this is, again, potential energy stored in the nucleus and those fundamental kind of bonding energies. And we will focus on, of course, our chemical potential energy, again, right, due to our structures, just kind of looking at how much is each bond worth. And so again, we have some equations and relationships. So this is useful. So kinetic energy is 1/2 mv squared. And then if we look at that, so now we can get to our units. So kinetic energy, or energy, is always in joules. And so let's look at the units for that. So if we look at this formula, so 1/2 mv squared, and so this is physics world. So mass is in kilograms, velocity is meters per second, and so if we plug that into this formula, we get meters squared over seconds squared times kilograms, and so that is equal to a Newton meter or a joule. So a joule is kilograms meters squared over seconds squared. So that could be useful if you ever get lost and need to figure out what a joule is. And then other important things that we'll need to know. So we'll have a calorie. And so depressingly, this is not your food calorie. So the little calories, so notice this is lowercase cal, is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And now I forgot what it is in joules. It's like 4 point something joules, blinked. And notice that 1 kcal is the energy needed to raise 1,000 grams of water 1 degree Celsius. And that is a food calorie. So that's a lot of energy kind of in your food, but now you can also understand how they quantify that. So if we were ever bored enough or needed another lab experiment, or if you're bored at home, you can burn your chips and food, and if you can quantify and capture all that heat, right, then you could figure out how much calories are in there. Oh, that's what I was looking for, 4.184 joules. So that's also, again, the temperature needed to raise 1 gram of water 1 degree Celsius. And so more useful conversions. So again, we have our 1 kilocalorie is then 1,000 calories, which is our food calorie. And then I can't remember if we necessarily do a lot of kilowatt hours in this class, but it does come up at least in other settings. So if you're ever asked about kilowatt hours, then it's equal to 3.60 times 10 to the 6 joules. All right, so now let's look at our first law of thermodynamics. So the first law is the conservation of energy. And so this means that the total amount of energy in the universe is constant, it is conserved, and so we can never design a system that will continue to produce energy without some source of energy. And so that statement, I always like to talk about these fun things. So have you guys heard of a perpetual motion machine? Or the idea of it? And so all we want to state is, right, that obviously that this is kind of some theory that somebody thought of, right? Can you have a machine power itself? Obviously, this is not possible since it violates the first law of thermodynamics. And so again, right, you can't just have a machine power itself. And so that's just kind of the fun thing about some of these theories. All right, so let's start with bond energies. So like I mentioned, we at least want to appreciate how much energy is in these bonds. And so chemical reactions, of course, involve breaking bonds in our reactant molecules, and then we might make new bonds to create the product. And so now we have this little symbol here, delta H, and so maybe we should define. So delta H is called enthalpy, so H is for enthalpy, which is really just a measure of heat exchange, at least when we're just looking at this enthalpy portion. So then it tells us we can figure out basically whether we need to put energy in or whether energy is going to come out by comparing the cost of breaking old bonds. So it costs energy to break our bonds, and then we will get income from making new bonds, since new bonds, any time you make a bond in chemistry, that's thermodynamically favorable. And so we'll use just like a standard bond energy table. So on an exam, I'll probably give you the bond energies so you're not like hunting around. And this is, again, just kind of for your knowledge how these are calculated. So they're in the gas state. And like I said, they usually just run computational calculations now. But at some point, right, they did some experimentally in the gas state to do some calculations. And then, of course, you can use computational chemistry to help you. It also assumes that they break homolytically, which, again, y'all don't have to worry about, but let's at least just define it so, again, we know what that means. And so most bonds are homolytic, which just means that, right, each one contributes one electron. So if you have H2 here, if it breaks homolytically, oops, I'm trying to use these little half arrows to show that each one gets one back out. So that's homolytic cleavage. And so technically you can have heterolytic cleavage. I'll just show one example. Again, we probably won't encounter that in this class. But compounds, so you can have these weird compounds. And I'm drawing it like so on purpose. But this is, right, ammonia is bound to BF3 here. And I drew it with this arrow to show, so again, right, we have ammonia with those 2 electrons. And boron, if you recall, right, it only has 3. So it doesn't have anything, right? I'm just kind of sketching out the Lewis dot structure. And so in this case, this is a weird scenario where nitrogen is actually contributing both electrons to that bond. So that would be a heterolytic cleavage and our heterolytic bond. So once you cleave them, nitrogen will get its 2 electrons back. But like I said, we won't see this in this class, but I at least think it's good that you're aware what homolytic versus heterolytic cleavage is. And so blah, blah, blah. So obviously, right, the actual bond energy may vary. But again, right, we'll just use our average bond energy to get our estimated change in enthalpy. And of course, obviously, it's going to work the best when the reactants are in the same state they are as they were calculated. So again, that kind of makes sense, but we won't worry about it too much for our class. So the important part, so probably star this, so bond breaking is endothermic. So now we're starting to define things, which means that we have to put in energy. So I'll kind of put that requires energy, or again, we're only talking about energy in the form of heat right now. So we're saying, okay, we're going to have to add heat or add energy to break this bond. And so again, that's endothermic, formally a positive enthalpy value. And then bond making is exothermic, and so that's going to release energy, and then that's going to formally give us a negative change in enthalpy value. Just kind of let everybody take that in, so that's important. And then what we'll be able to do is we'll take our total number of our bonds broken, and again, right, that should be some positive value from breaking that, and then plus our bonds form, so that's going to be some overall negative value, and then that gives us our total change in enthalpy. And so now we just want to compare bond energies to give us, again, a sense. And so, of course, the more electrons they share, the stronger the bond. And so this is just to highlight the differences between a triple bond and a single bond. So all we want to say is, okay, well, a triple bond is going to have more energy. That's kind of expected. And then, so the shorter the bond, the stronger the bond, again, typically. And so this holds true, for example, our halogens. So bromine, bromine, again, right, you have some physical limitations there. And so it's 193 kilojoules versus a bromine-fluorine bond. So again, fluorine is just a little smaller, so it can be a little tighter. And so that gives it a slightly stronger bond. And then again, just in general, they get weaker down the column, but stronger across the period. So that kind of makes sense, right, as they get more electronegative. And then obviously they get weaker just from slight radius effect. And again, on an exam, I would probably give you just the individual bond energies. Otherwise, this is kind of a typical bond energy chart. So ones that you should find in your textbook should hopefully be in kilojoules per mole. Again, that's just kind of our standard unit. But just pay attention to other units. So you may see like electron volts or something else. So just watch out, you know, if you start Googling other resources or whatnot, right? So it could give you bond energies in other units. And again, these are per mole. So sometimes you might see a bond energy like, you know, per atom. So again, just make sure that you're in the correct units there. All right, let's see if we can at least do this example before break here. And so let's go through this diagram of what it's trying to show us. And so what we're trying to look at is this reaction with methane and chlorine to give us chloroform and hydrochloric acid. And so first we might want to write that out. So CH4 plus chlorine gives us chloroform. And for initially doing these, you might find it useful to kind of draw out the structure. Okay. And so then what we're trying to look at, and this is where drawing out this methane maybe helps us. And so what they're showing is, right, well, first we need to put energy in to breaking our bonds. And so that's the first thing that we're doing in this analysis is what needs to break. And so looking at this, right, obviously we need to break one of these CH bonds. So it's going to become a carbon-chlorine bond. And then we're going to break a chlorine-chlorine bond. And it does show that there, but we can do that now mathematically. And so I like to separate it, kind of bonds broken then. So then we have 1 carbon hydrogen and 1 chlorine chlorine. And so now this is where I use my chart. So now I'll go back to my chart up here. So where's CH? So CH bond 414. So let me just write that down. And then chlorine, chlorine, go back up. There's chlorine. So 243. Okay. And we could even go ahead, right, and add this up. Let me just get out my calculator. So far we have that we had to put in 657 kilojoules of energy, right, to break those bonds. And so that's, again, kind of what they're showing here. So our little diagram with our plus arrow to indicate, right, we put in enthalpy. And so now let's see how much we get back. So again, right, helpful to draw it out and just kind of analyze what we made. And so, of course, we made a carbon-chlorine bond. Sorry, that looks like I wrote chlorine-chlorine. So carbon-chlorine bond there and an HCl bond. And so now let's add up our bonds formed. So we have 1 carbon-chlorine and 1 hydrogen-chlorine. And so let's see, our carbon-chlorine is 339. And then our HCl is 431. And remember, this is going to be negative, so how much we got out once I finish adding. So 339 plus 431. So then that gives us 770 kilojoules, but again, that's negative since we got it out. And so now we can add these two numbers together. So now I add negative 770 plus 657. So now I get overall negative 113 kilojoules. And so overall this is telling me, since it's negative, that it was exothermic. And so we can kind of see that in this diagram as well. So they didn't quantify it for us using numbers, but they did show us that our products are lower in energy, so then we expect this to be an exothermic reaction, which this is showing here. All right, so that's a good point for a break. So I'm going to leave it here. So we'll pick back up with this problem, and we'll kind of repeat that same process, right? Like I would draw out your methane, your 2 waters, your 4 hydrogens, and figure out who was broken and who was formed. But all right, we'll take our break. Now be sure to grab homework lab. So as you kind of get back from break, you can start outlining this problem, and then if you need me to scroll up to get some bond energies, just let me know. So maybe you want to copy this down, and then y'all can tell me to scroll up in a little bit. And then I'll kind of scroll up. Let me know. And then the kind of tricky part is you have a weird exception here. So most CO bonds are 736, but then it does mention that CO2, you should use this number of 799 there in the corner. So I'll try to zoom out so you can see it. If you can't read it, I can zoom in or... I just posted the live notes on Blackboard too. So let's kind of see where we're at, and yeah, keep going if you're still working on it. And so I'm just going to kind of draw out our molecules first. And another thing to point out is, right, we are starting with a balanced reaction. So just kind of, again, right, double check that before you start going too deep into a problem. And so I'm just sketching it out again so we can really see how many of each bond is being broken and then formed. And so a little explicit, right? But again, I just want to show every H2 so we can see. And then CO2. All right. And so then what did y'all get? So which bonds do we have to break, and what did that equal to? So what do we notice here? Yeah, so right, so it looks like, so you're telling me we got to break all these bonds, right? And then you said, well, we also got to break all these bonds to eventually get CO2. So yeah, exactly. So that's, again, the value of kind of drawing it out is so we can see. So now, okay, I have 4 CH bonds that have to get broken. And then, again, this is where the drawing helps, because then we have 4 OH bonds, right, that we have to break. And so let's just get those values. So CH, 414. And then OH, is 464. And then, of course, times 4 times 4. So, right, this is, again, you have to account for how many of each bond. And so, excellent. So, I see it in the chat, too. So, yes, you just add everything up here. I'm punching it into my calculator. And so we get a total of 3,512, right, kilojoules that, again, we put in to break all these bonds. And I'll put a big plus sign. So again, right, showing that's energy going in. And so now we just kind of have to repeat that. So again, like it was mentioned, okay, we're going to make this new CO compound. So we have 2 CO double bonds and then 4 HH bonds. So now let's figure out, right, how much we got back from our bonds formed. So CO times 2, so that was a weird 799 value that was specifically for CO2. And then let's look up a hydrogen bond. So 436 for each hydrogen. So 799 times 2 plus 436 times 4. And so I get 3,342 back out, and so that's a negative. Since again, right, exothermic. So thermodynamically favorable. And then, so of course we can figure out, right, our total change in enthalpy for this process just by adding these two numbers together. So again, make sure you make it negative now. Oops, sorry. Times -1, there we go. Plus 3,512. And so we overall get 170 kilojoules for this process. And I'll put again a big fat plus sign so we can tell that that's energy that overall needs to go into this reaction. So that's telling us that this is an endothermic reaction. So it's going to require heat, and it would feel cold to us, though. Questions on this and on the process or anything? So you'll probably have a question like this on your exam, but like I said, the bond strengths will be provided. All right, let's keep looking at this. And so we kind of touched on these terms, but now we're going to look at them. And so again, in an exothermic process, we're seeing that formally our products are lower in energy. So products lower in energy. And so all that means is, of course, that heat has to go somewhere. And so this goes back to our first law of thermodynamics. And so basically we're saying, okay, this is our system here. And if it's exothermic, that means that that energy has to flow somewhere. And so that means that it will flow into our surroundings. So then again, it's going to feel hot to us. And so those like instant heat packs are like those hand warmers. Those are examples of exothermic reactions. So those hand warmers are usually like a little iron powder, and then they get exposed to the air. And so of course they undergo redox reactions that makes them feel hot. Or other like hot packs can feel hot, again from the same sort of thing, activating an exothermic reaction. And then this is another important form of our diagram. Again, let's label it. So exothermic. So again, products are lower in energy. So again, we can see products minus reactant, potential energy here on our side. And so that would give us a negative number. And again, right, that heat is released, and we're going to feel it. So again, if we're feeling an exothermic reaction, right, it's going to feel hot. Let's look at other pieces of this. So of course we have our reactants, again, just where they're starting energetically. Then we have our activation energy, and so this is just the energy that's needed to kind of get our reaction going and getting it into this transition state. And so this transition state can be just like where the molecule is essentially reacting. It's high energy and fleeting. So for example, if we were thinking about this reaction, the methane, or not this one, sorry, thinking about this one, our methane and chlorine. So then thinking about the transition state of that one would be kind of this weird transition where it has, right, essentially kind of 5 things attached to it. And this one is probably leaving, and the chlorine is coming, but it's technically kind of some weird, 5 5-member temporary state and probably draw some dashes, right, to show that something's breaking, something's coming. So this would be the example of the transition state. Again, obviously that's going to be fleeting, and then it leads us down to our products. So again, right, exothermic, our products are lower, and then this difference in energy here is our change in enthalpy. And then endothermic is obviously similar, but the opposite. So now our products are higher in energy. So again, showing that we put energy into the system. So now, right, you can think about like those ice packs that are instant. So I believe those tend to be like ammonium chloride, and then you break the barrier and there's water in there. And so that tends to be cold. So, right, it feels cold to us, since then our body is supplying that heat necessary, right, to dissolve the ice pack in this case, or whatever endothermic process is going on. And so again, right, we see that in this diagram. So energy is flowing into our system. So again, our hand is the surrounding. So it's going to feel cold to us as that energy flows from our hand to the system. And so pretty similar energy diagram for endothermic reaction. Obviously the key point being that now our products are higher in energy, and so this change in enthalpy corresponds to the energy absorbed then. And that again, it took from our hand or the environment. And so same thing. So reactants start off on our left side over here. Then we have, right, our activation energy that goes all the way from our reactants to our transition state once again. And then change in enthalpy from reactants to products. And again, products higher shows us that it absorbed energy there. And so then we have kinetics. Again, we're just kind of taking a quick approach to kinetics in this class. And so kinetics is just vaguely defined as our reaction rate, so how fast or how slow a reaction is. And so with the rate, the important part is it's something that we have to measure. So you have to back it with some data, right? We can't just look at a reaction and predict if it's going to be fast or slow. Whether it's endothermic or exothermic doesn't dictate either how fast it is. It's separate processes. And again, right, we're just kind of taking an overview, but obviously you can imagine where you want to be able to control the speed of the reaction, or even just thinking about how quickly it's going to react. I mean, this can go all the way from industry, right, and trying to figure out how to design something, or just even in lab if you're adding some reagent. So for example, even quenching a reaction with like water or isopropanol, you want to do that slowly so that you don't have a bunch of release of gas or something. Or if it's very exothermic, right, you might want to add the chemicals slowly. And so again, just kind of a general overview. So in general, the greater the concentration, the faster the reaction. So I think you'll be testing that in lab this week, just kind of playing with different concentrations. And so again, if you have increased concentration, this tends to increase the frequency of collisions. And of course, more collisions leads to more successful reactions. If we were dealing with gases, but again, we won't play with gases personally in here. Gases just get dangerous for other reasons, but your pressure is obviously going to be related to your concentration. And so the higher the pressure, the higher concentration. Again, same thing, kind of more collisions. And then this kind of teases, I believe, is our next chapter on molarity. And so molarity will just roughly define as moles over liters. So this is all that it means. And so all we're saying is, again, right, the greater the molarity, the faster it reacts. And so you'll compare that, like I said, this week. I think you're looking at 1 molar, 2 molar, and 3 molar HCl solutions and seeing which one dissolves the magnesium the fastest. And so now you're starting to understand better what these little M's mean when you're reading the bottles in lab. And so again, we have this temperature relationship. We can quantify it. We're not interested in doing that in this class. So if you want to quantify reaction rates, you can take the 200 levels class and have more equation fun. Otherwise, we just kind of say, okay, in general, for every 10 degrees Celsius rise in temperature, the speed doubles. Again, that's just a very general statement. Again, you'll see this in lab, just kind of, you'll heat some reactions, cool them, and just kind of see what goes faster. And so, blah, this Arrhenius relationship, like I said, this is probably more for the 200 level course, but this is just to say, right, there is a mathematical relationship. It does exist, but again, beyond the scope of kind of this course. And so with this, so you kind of get, it's kind of funny because we take like, all of these are separate chapters in like the 200 level. But again, here we're just kind of taking a quick and dirty look at thermodynamics and equilibrium and everything. And so we'll look at equilibrium as well in our lab. And so let's kind of look at equilibrium. And so we start off with analyzing this kind of reaction here and what's going on. And so this reaction gives us a look at what's going on right in our bloodstream. And so basically what happens, and we can think about when your hemoglobin shows up in your lungs, right? And it's probably oxygen deprived at this point, but then your lungs have a high concentration of oxygen. And so because you have a high concentration of oxygen, this of course causes the oxygen to bind to the hemoglobin in your lungs. Then it travels out. And so let's kind of keep thinking about this process. And so now kind of right in your leg or wherever. And so once it gets to your leg, it tends to be, right, an oxygen deprived environment because obviously, right, your muscles are using that oxygen. And so now we'll put, right, there's no or little O2. And because there's a lack of O2, once your hemoglobin shows up to your leg, it's going to release it, right? And so now we're starting to see also the definition of equilibrium. So equilibrium and these kind of double-headed arrows, right, describe a reaction that can go forwards and backwards. And so this is obviously a little different than what we're used to, right? So normally we're looking at those single-headed arrows and our product, right, our reactant fully converts to our product. But instead, again, right, we're looking at these equilibrium reactions, and you'll get to play with them in lab, like I mentioned, and kind of see how you can stress them out to cause them to do things. And so again, right, just thinking about how this works. So obviously your oxygen gets deposited in your leg, and then the hemoglobin, right, goes back to your lung, and repeats the whole dynamic equilibrium process again. And so like we had mentioned, we've mainly seen the single arrow, and so all that indicates is that, right, all of our reactants are converted to product molecules. And so some sort of double-headed arrow indicates that there's some sort of equilibrium, or again, right, that you can kind of manipulate this reaction to go backwards and forwards. And then we do want to be able to at least kind of write out our equilibrium expression. So I won't ask you all to do too much with it. Like I said, if you are interested in quantifying this and doing way more equilibrium, take the 200 level. And so this is our relationship here. And so notice we have some general equation. The little letters here represent our coefficients for a balanced equation. And then our A, B, C, D is our, whatever our molar concentration is of our, in this case, products over reactants. And so notice, right, it's products over reactants, and then you take everything to the power of the coefficient. And so again, this concentration is usually in molarity, or the other case would be partial pressure. But again, I'll try to probably stay away from partial pressures for the most part, at least in this context. And so K does not have units, so it's just a ratio. So do we all have this form written down at least? All right, so then looking at this, we can practice kind of writing our expression or see how they got to it down here. So again, write products over reactants. This is our balanced equation. So we take NO2 to the power of 4 times our concentration of O2, obviously to the power of 1, and then over our reactants, so N2O5 to the power of 2. And then, so the only other thing that I might make you do is ask you to calculate this. And all I would say for that is, okay, so at equilibrium, the concentrations are as followed. And so I'd have to give you, so let's just say NO2 is 0.567 molarity, O2 is 0.333 molarity, and our N2O5 is 0.101 molarity. So see if you can just plug that in, kind of what that would look like, right? So then you're just plugging these numbers into that expression. And so like I mentioned, so we just have to plug it in, so I'll write it just kind of how we plug it in. So K equals, so then we have 0.576 to the fourth times 0.333 times 0.101 squared. So then just punch that into your calculator. So then we get something of a K of 3.59. And so again, right, this is probably the most that I would ask you to do with this K. But then we at least kind of want to appreciate what they're trying to show us with K. And so what does this value of K imply? And so if we're looking at this reaction, so H2 plus bromine gives us hydrobromic acid here. And so again, look at how they set it up. So roughly looking at products over reactants. And so if we look at this number, and obviously this is a pretty extreme case, so we have K of 1.9 times 10 to the 19th. Well then, again, right, products over reactants, pretty large number. So this is telling me that the products are highly favored, right? So it's probably going to go almost to completion, and only a very small amount of reactants will remain unreacted. Yeah?
Do you need to know the Lee-Chattan's principle?
Do you need to know what, sorry?
The Lee-Chattan's principle. Do we need to know it for this module?
Yeah. So you have to know the basics of Le Chatelet's principle. Well, that has to do with, again, stressing, but. So lab will give you a better sense of just the qualitative aspects of Le Chatelet's principle. And then, of course, if our K is much, much less than 1, so again, looking at another extreme case, so K is 4.1 times 10 to the negative 31 for this reaction of N2 plus O2 gives us NO. And so again, that makes sense for this reaction, and that's probably a good thing if we think about what this is saying. And again, products over reactants. And so since our number is pretty small, that means it favors our reactants, which is good for all of us breathing people, since, right, if this reaction was favored, we would have no oxygen left to breathe. So that's a little awkward. And then, of course, right, we kind of saw it in this case. If it's close to 1, you know, then it's really not favoring one extreme or the other, and you kind of have more of that, right, back and forth type equilibrium. All right, so then with that, we want to talk about Le Chatelier's principle. And so all this is kind of saying, like, can we predict which way our reaction is going to go? And so a couple of things to start off with. So, okay, once our reaction is at equilibrium, then our concentrations of reactants and product stay the same. So again, right, this isn't saying that the reaction's done. So at a molecular level, they're still going, they're still popping back and forth, but it's just overall, they're unchanged. And then if we do change the conditions, so this is part of Le Chatelier's principle, then of course the concentrations will change until equilibrium is restored. And again, I'll just put K as the same. So K won't change, although, like I mentioned, you really won't have to worry about that in this class. If you're in the 200 level series, you'd be quantifying all this. But like I said, we just need to kind of be able to predict which way it might shift. And then we'll kind of explain what this means in a second. It'll make more sense when we look at a diagram. And basically, though, right, we can have new equilibrium concentrations, but our equilibrium constant will always be the same unless we change the temperature. But again, right, a little beyond this class. But we do want to predict, again, the effects of these changes and be able to predict, am I going to get more products or reactants? All right, so let's start to go through these. We'll see how far we get. And again, ask questions, because this has a lot of words. So let's try to see what it's saying. And so let's kind of look at adding reactants, but let's scroll down to this here. And so we can look at technically this side. And so if we look at our reaction here, so we're looking at some sort of dimerization reaction. So we start off with our dimer, and then it dissociates. And so again, right, okay, all it's saying is initially we're at equilibrium, so concentrations are remaining the same. Like I mentioned, you can still have this dimerization going back and forth, right? This reaction is still occurring. It's just, again, your overall concentration will be unchanged. And so now we've disturbed the equilibrium. And so that's always what's kind of meant with these Le Chatelier's questions, right? Is we have a system in equilibrium. Now we're going to do something to it and perturb it. So in this case, just by how they've set up the reaction, so we're adding our reactants. So we can see that, right? So we have this large artificial spike, obviously, from somebody dumping in some more reactant. And so now we could go back to the words for a second, just so we can kind of see what the heck they're trying to explain to us. And so it says, okay, as if a reactant is added, as long as it's included in our equilibrium expression. And so this is also kind of confusing, so we'll look at this because it makes some caveat as long as it's not a solid or a liquid. And so what it means by that is if you have like a solid reagent, like a pile of carbon or something, and again, we'll look at some cases. So, right, if you just have like a solid reactant, then obviously, right, there's not a concentration. It's just like a large pile of stuff, and it's not going to be concentration dependent. So same thing with a liquid. So this would be if you're using like a liquid reagent itself. Sometimes these are called neat reactions if you don't have any solvent. So now I'm like blanking. So obviously if you have water in there, that's not going to be part of it. But any other like organic, totally blanked on this reaction that I do. It's the nylon reaction. If we had any reagents, I'll just put liquid reagents instead of trying to name some. But basically, right, if you have a liquid reagent, it's not being added as a molarity, right? So does that make sense? Maybe we should look up. So I'm just trying to point out. So like, let's just say you had ethylene glycol. And the only reason why I picked ethylene glycol is because it's a liquid, right? So like, it's just saying if you're using a pure liquid reagent and you add it in there, right, it's not going to change the concentration. But again, generally, we're not kind of working with that, right? So in lab, you're usually working with solutions. And so like I said, you'll see that on Wednesdays. So in lab, right, you might have some iron 3 solutions that are 0.1 molar, etc. So that would be good. Or you'll work with thiocyanate, again, right, different molar concentrations. So that's different. Does that make sense to everybody? Kind of what it's referring to. So again, it just can't be a pure solid or a pure liquid reagent, as long as there's some sort of concentration to it. All right, and so then back to these words again, right? We're trying to look at what they're saying. So adding a reactant initially increases the rate of the forward reaction, and that kind of makes sense, right? So you have a lot of reactants, and now it's going to pump out some more product. No official rate on the reverse reaction. Well, that makes sense. And then it's going to proceed to the right until equilibrium is restored. Right? So again, that kind of makes sense. So we're going to add reactants. So then we're kind of forcing it to make more products temporarily until we get equilibrium. And we can see that again in our picture now, what it was trying to say. So then it's saying, okay, right, our forward reaction is increased, and we can see that. So now we're making more NO2 to kind of compensate, right, for all this N2O4 that was added. And then now, right, once their overall concentrations are remaining unchanged again, then we have our new equilibrium established. And then, of course, because we added, right, more N2O4, and so sometimes it makes these weird statements. Let's kind of read them, but then we'll see what it means. And so, right, it has this long sentence here. So at the new equilibrium position, you'll have more products than before. Okay, well, that makes sense, right? That's what it's saying. So yes, we have more products, right, than what we started with. And then it makes this kind of, I think it's kind of a weird statement, less of the non-added reactants than before and less of the added reactant. So if we had had another reagent, right, obviously that would be consumed. And then less of the added reactant. Well, all that's saying is, okay, well, we did artificially, right, kind of dope it up to here, and then it was kind of consumed until we reached equilibrium. So that's what it means by that, right, that some of it was consumed into making new product. So we have a little less than what was added. And then, like I said, obviously in this case it doesn't work since we just have this dimer. But if there had been another reactant, right, this would be lower in concentration. And so again, right, K is not affected. And then of course, if we remove, reactants or products. Again, same sort of concept. So we can look at this one. So in this case, in this other scenario, so now we've added more product. So again, right, we've artificially doped it. Now it's going to make more N2O4, of course, drive that reaction forward until equilibrium is established. And so kind of the practical use of this tends to be for condensation reactions. And so condensation reactions are anytime you're trying to put two bonds together. And so basically you have kind of A plus B gives you this new AB plus water. And so that's the key point of these condensation reactions, is that you're losing something to form water. So generally like some amine plus whatever. And so then you would lose an H and an OH to make your bond. So something like that is how it looks. And so how chemists use this, I feel like, I've showed a Dean Stark before here, right? Have I showed you all Dean Stark? I thought we've looked at a picture, maybe not. So let's find a good picture of a Dean Stark. So this is at least kind of a general diagram. So the idea with these reactions and how we use Le Chatelier's principle is you have your little flask, right, boiling your reaction here. And condensation reactions tend to be slow by nature. That's why you have to drive them. And so it's boiling, it's happy, blah, blah, blah. So this is a condenser up here to cool our liquid back down. And so what you'll notice is it has this little side thing. So this is the Dean Stark, this side thing over here. And so it's basically kind of like a short burette. And notice how it has a stopcock down there so that you could release some liquid. And so the idea with your Dean Stark is that you're boiling it over time. And so then, again, you kind of have to plan this a little appropriately. Not every solvent will work, but most organic solvents are lighter than water. And so you should have a nice layer of water on bottom. And, you know, if you have your organic, it'll be on top. And so, again, you would drain out the water then using your Dean Stark here. So you could drain some out, right? And then Le Chatelier's principle now is in effect. So, okay, if we're looking at this general reaction, we've removed the water, right? So now that's going to want to drive that reaction forward so we can keep making more water product. Again, obviously, right, we're not interested in that, but just by using Le Chatelier's principle and continuing to drain out this water, that will continue to drive this condensation reaction forward. And so just to give you some context, like some condensation reactions, you know, they can run for like 2-3 days. So that's, you know, quite a decent time of heating. And so, you know, periodically the chemist will go and drain the water out just to keep that reaction going and get a high yield. So that's how you would use Le Chatelier's principle, you know, kind of in real life. So this is the most common example. But again, obviously, if you were to go on and do industry, you'd have a lot more to think about of like, how do I manufacture my product efficiently and all those things and control the reaction. All right, that's probably a good place to stop. So I think we just have a little bit more. So we'll talk about catalysts on Wednesday, but then we'll spend the rest of the time, we can do some practice problems. So if you have redox questions too or anything else, we can work on that. And of course, we'll do our quiz on Wednesday as well over last week's stoichiometry. So again, I'll see y'all in lab, and then just let me know if you have other questions.